Hi everyone. In continuation with our lecture series on the analysis of CMOS digital circuits, I thought I'll spend a few lectures on the analysis of capacitive charge sharing circuits with MOSFETs in between them in place of resistors. Now, before we go, I'll analyze a set of very interesting questions. But before we go to that, I'll just lay some groundwork, which will be very helpful in analyzing those circuits. Now, for some of you, it might be very trivial. You can skip towards the problems directly, but I recommend you just bear with me for a few minutes before we go to solving those problems. The one important condition that you need to be aware of while solving those problems is the conditions under which the drain current becomes equal to zero. I'll show this for an NMOS device. Same things hold true for a PMOS device as well. So there are two conditions under which the drain current of a MOSFET can go to zero. One is the cutoff condition, which is your gate to source voltage is less than or equal to VTN, which means there is no inverted channel at all. Between drain and source, there is no inverted channel, even though there is a finite VDS, which means there is a finite electric field between drain and source. But since there is no channel, there is no conduction, so drain current goes to zero. The other condition is when VDS equals zero, which means here I'm assuming VGS is greater than VDN, which means there is a channel. But if VDS equals zero, there is no horizontal electric field to move the carriers in the channel. So only if the carriers move in case of an NMOS device, electrons move from source to drain, you'll have a current flowing from drain to source. Otherwise, there is no conduction. So that is the other condition for drain current becoming equal to zero. And of course, the third trivial condition is the combination of both. You simultaneously satisfy both the conditions, even then there will be no conduction. So before I'll explain that on an ID versus VDS graph, but before that, we will look at this on the MOS device structure. So I've shown a cross section of a MOS device. The one on the left is a condition when VGS is greater than or equal to VT. So which means, if you recall, there is a vertical electric field which draws the electrons, or in case of a MOSFET, it draws electrons to the surface. So the channel, it's a p-type substrate. It becomes n-type near the surface. It's filled with mobile electrons. Okay, and then because, if you apply a horizontal electric field, then there will be a current in this device. But if your horizontal electric field is zero, that's what the VDS equal to zero condition implies. The horizontal electric field is zero. So therefore, there is no movement of carriers between drain and source. So therefore, there is no drain current. Even though the channel is present, there is no movement of carriers between drain and source because the horizontal electric field is zero. That is nothing but, in terms of, if you want to say that in terms of voltage, VDS is zero. The other condition shown on the right is the case where the horizontal electric field is finite. It's non-zero. Ex is finite, but your VGS is less than or equal to VDN, which means there is no inversion channel. Even though there is an electric field between drain to source, there is no channel of mobile carriers to move between these two terminals. So therefore, even then you have a drain current becoming equal to zero. You can easily show that on an ID versus VDS graph. On an ID versus VDS graph, the x-axis is what we would call the line when VGS is less than or equal to VDN, which means ID is zero no matter what your VDS is. Your VDS can be anything in between 0 to VDD, but if your VGS is less than or equal to VDN, no current flows through this device. Now, since you know the ID versus VDS graph, we plot ID versus VDS for different values of VGS. Whatever be the value of VGS, if your VDS is zero, so that's this point here, if your VDS is zero, all these graphs converge to ID equal to zero. If your drain to source voltage is zero, there is no lateral electric field to push the carriers between drain and source. So therefore, there will be no current conduction in that case, and the current will come to zero. So I'll take some very trivial examples to discuss that. So first case is an NMOS device. I've connected a fixed voltage source between gate and source. So your VGS is always equal to VDD. And at the drain terminal, I've connected a capacitor charged to VDD. Now, what will be the condition under which the current in this MOSFET will come to zero? So immediately you can see VGS is finite, VDS is finite, so a drain current is set in the MOS device, and immediately this MOS current flows and this will discharge this capacitor. It will keep discharging the capacitor as long as the current in the MOSFET is finite. Okay, since VGS is fixed here, when VDS, the current in this MOSFET will go to zero only when VDS is zero. So which means when the capacitor is fully discharged from VDD to zero, that's when the current in the MOSFET will go to zero. I can show that on an ID versus VDS graph as well. Show the same circuit here. So we can assume this is the graph which corresponds to, say, VGS equals VDD, and on the x-axis this point, say, is VDS equal to VDD. As the device starts conducting, it's discharging the capacitor, which means the drain to source voltage is decreasing. So you will move along this line on this graph, and eventually you will come and join at this point. You will eventually, when VDS becomes equal to zero, the drain current also becomes zero. So you will be traversing along this graph here. Okay. Now I will analyze another circuit where I have a MOS device. The drain I've connected on one terminal is at 2 volts. The other terminal is connected to a capacitor with 0 volt, and gate is at 2 volts. Now I've said MOS, in a MOS device, the gate and drain and source are defined by the potential that you apply to them. So whichever is at a higher potential, that becomes drain. So this is drain and this is source. You can see VGS is 2 volts and VDS is 2 volts. And the VT of this device is, say, 0.5 volts. So the device is conducting because both VDS and VGS are finite. Now for this device to be turned off, either VGS should become less than or equal to 0.5 or VDS should become equal to 0. Whichever condition is satisfied first, that will dictate the steady state voltage across the capacitor. So now you can see there is drain current which is going to flow from the 2 volt source to the capacitor. So the capacitor voltage increases. As the capacitor's voltage increases, the source voltage is increasing. Now since the source voltage is increasing, both drain VGS and VGS is reducing and VDS is also reducing. Both are decreasing. Now whichever reaches the first condition for cutoff, that will end up dictating the steady state voltage across the capacitor. So we can see as the source voltage decreases, now the two possibilities is that this capacitor can at max go to 2 volts. So when it reaches 2 volts, VDS becomes 0. That is the maximum voltage this capacitor can go to. But at that point, your VGS becomes 0. So which means your MOSFET stops conducting much before that. So as this capacitor voltage is increasing, and say it reaches 1.5 volts. Okay, 1 VT lower than the gate voltage. When it reaches 1.5 volts, at that point, you end up satisfying the condition VGS less than or equal to VT. So at that point, the device enters cutoff and the current conduction stops. So the capacitor voltage will stay put at 1.5. Okay, so if let's say I raise the gate voltage to 3 volts. If I raise the gate voltage to 3 volts, then of course this voltage can keep on raising further. It will keep raising, and when it reaches 2 volts, your VDS will become 0. VGS will still be finite. VGS will be 1 volt in that case. Okay, and it can still reach 2 volts. It can reach a maximum of 2 volts, but in that case, the condition which dictated the steady state is VDS equal to 0, not VGS less than VT. But if I have 2 volts in place of 3, then this capacitor cannot go more than 1.5, so the steady state will be just 1.5 volts. We can also see that on an ID versus VDS graph, but I'll just probably explain very briefly. So we'll initially start at this point. VDS is 0.2 volts and VGS is 2 volts for this device. As the source voltage decreases, both VGS and VDS will decrease. And when the source voltage reaches 1.5, your VGS becomes 1.5 and VGS becomes 0.5 and VDS also becomes 0.5. But since we have reached cutoff, the current in the MOSFET already becomes zero. So this is how on an ID versus VDS graph, the trajectory of the operating point or the drain current of the operating point of this MOSFET is going to look like this. It will be a combination of this points. If I just join these points on the green curve, that's going to be the trajectory of the operating point of this MOSFET here. The other condition, again, it's an extension of what I had solved previously. The gate is connected at 2 volts. The drain is at 1 volt now. Now, immediately we can see a current will flow. So this is source. So there is VGS of 2 volts. So a huge current flows through the capacitor and the capacitor voltage will start increasing. As the capacitor voltage starts raising, now for this device to be cut off, the capacitor voltage should be 1.5 volts. For VDS to become equal to 0, the capacitor voltage has to be just 1 volt. The moment it reaches 1 volt, then there is no VDS and the current in a MOSFET goes to 0. So the steady state voltage across the capacitor will stay there at 1 volt. So that's why I said it's useful to know the conditions under which the drain current in the MOSFET goes to 0. So that's all that was needed to solve this too. Okay, so as the source voltage is increasing, both gate to source and VDS is also both are decreasing. But first VDS becomes 0. Okay, VGS has not come to VT yet, but before that VDS became 0. So therefore the drain current became 0. So once the drain current becomes 0, there is no transfer of charge from the voltage source to the cap. So the voltage across the cap will remain fixed at 1 volt. Okay, we can show that on an ID versus VDS graph. You start from, say, this is 2 volts of VGS and 1 volt of VDS, and both VDS and VGS decrease, but before VGS is still fixed. I mean, this is the graph, say, corresponding to VGS equal to 1 volt, but VDS has by then become 0. Okay, so the device stops conducting and the capacitor voltage stays at 1.